Okay, hi. Thank you for being here. This is our last Cosmic Conversations talk of the year, and we have Jaymie doing it this time, our very own head of the postgrad committee, master student with Dr. John. Yeah, and he's working mostly on structure formation and those sorts of things. So thank you, Jaymie.
Yeah, thanks everyone for being here. I just want to make a note on Nana, actually. So when we started Cosmic Conversations last year, our idea we had for it and our execution was certainly not what it should have been, and what we envisioned for it, at least when Nana took over this year, we kind of brought our idea and turned it into what we wanted it to be. So just thank you for that. So yeah, today's talk is basically just an introduction to cosmology. The idea here is to introduce you guys to some of the basic concepts. None of this is going to be particularly technical. We're going to focus predominantly on large-scale structure formation. So this is not at all an exhaustive talk on all of cosmology. It's an introduction and also mainly focused and geared to what it is that I'm particularly concerned with. So yeah, so we'll do a quick history of the universe. We'll talk about some of the background cosmology, introduce the idea of inhomogeneities and why they're necessary, and then we'll go into perturbation theory, structure formation. And I actually took the slide out for cosmic tensions because I think I'll just talk about them as we go along. There's only really one that I want to mention anyway. So this is a really cool diagram of the history of the universe. It's actually one of my favorites. And essentially, the Lambda-CDM model of the universe, which is our best understanding of how the universe works, is sort of catalyzed by the Big Bang. And so a lot of physics happens from the Big Bang to present day. And so there are just a couple of landmarks I think that are nice to highlight. So for example, in the first second of the universe, you have a lot of things happening. I think you have the QCD phase transition, you have electroweak symmetry breaking, very technical particle physics stuff that I'm not so clued up on, but there is, after about a second, you have what is known as neutrino decoupling. And what is interesting about that is, in the same way that we can see the photons that decouple at recombination, and we see them in the CMB, we could potentially also see the neutrinos that decouple. And if we can do that, we could see the universe when it was only a second old, and that would be a very cool thing to be able to see in terms of either verifying or falsifying some of our theories about the early universe. And then after about 380,000 years, you have recombination. So this is just when the universe started, as we all know, in a hot dense state. And as the universe expands, the temperature drops. But the mean free path of the photons is very short initially because everything is super dense. So they keep scattering off all the electrons. Eventually, things are less dense. And so your photons end up streaming freely into the universe. They propagate straight through the universe. And those photons are the ones that we actually see in the CMB. Then you have the cosmic dark ages, which is quite cool because that basically is the, I don't know how many years, that's about 100 million years, where it's called the dark ages because there aren't any stars. So there's no lights in the universe. And then after about 100 million years, you have the formation of the first astronomical objects. This was important because it starts the epoch of reionization. So you have your first stars. The stars emit ultraviolet light. They ionize the surrounding interstellar gas. And on top of that, what's also important about them is that when these stars, for example, blow up in supernovas, they actually started dispersing much heavier elements into the universe. So instead of just the production of hydrogen and helium that was from the Big Bang nucleosynthesis, you also now have heavier elements going into the universe. Up until about a billion years after the Big Bang, the universe is fully ionized. You have essentially your first galaxies are formed. And from then onwards, you have up until about 13.8 billion years. Till today, you have the formation of the rest of the universe. So all of the large scale, the galaxy clusters, etc. And so some fundamental things that fundamental observations we talk about in cosmology. One is actually, I stole this a bit from Barbara Leiden's book. It's based on Olber's paradox, which is that if the universe is infinite and static, then there should be, in every line of sight, there should be stars. And so at day and at night, our sky should be lit up with stars. But of course, when the sun goes down, it's pretty dark. And so one can only appreciate this if you realize that in that paradox, the assumption that the universe is static is a bit of a problem, right? The universe is expanding. And so the reason, one of the big reasons that the night sky is so dark is that there are some objects that are so far away that their light hasn't actually had time to reach us, right? And then we also have large-scale homogeneity and isotropy. This is a big thing that we'll talk about. So that basically just means that it doesn't matter where you are in the universe or in what direction you're looking, it's the same, right? So put your telescope on one side of the universe, upside down, or on the other side of the universe, and upside down, the universe exists. And then one of the great sort of observational breakthroughs was Hubble's law, so the fact that the universe is expanding. And so this is best described through his plot, the Hubble plot. So they found that the recession speed of velocities was proportional to their distance from us. So you have the galaxies that are very far away, so they're very high redshifts, and the further away they are, the faster that they're moving. And the slope of that plot is the Hubble constant, as it's known, but it's essentially the Hubble parameter evaluated at today. So subscript 0 means its value today, not its value at the start. As typically in physics, we like to use subscript 0 as the start. It is its value today. And here is just a whole bunch of observational parameters. So we're not concerned with, I'm not going to be very concerned with most of them actually. And there's all sorts of likelihoods that you can use of Bayesian statistics and stuff to actually compute the values of these things. And these are sort of the generally these are the accepted cosmological parameters, except for a few of them that have some sort of discrepancy in their measured values between different types of experiments. But if you want to theoretically develop a model, if you want to develop a theoretical model of the universe, you need to both describe its geometry and you also need to describe its matter content, right? So the geometry for our universe is described by the flat Friedmann-Lemaitre-Robertson-Walker metric. I'm just going to call it Robertson-Walker. And so it is the most general four-dimensional metric that has embedded in it the assumptions of homogeneity and isotropy. Typically, it also is comprised of a curvature parameter as well as a radius of curvature, but we see that the total contribution of curvature to the total energy density of the universe is much less than 1% even. So we assume, at least in our theoretical model of the universe, that we can use a flat metric. So it basically reduces to equation 1, and then the scale factor, which is the A, is what parameterizes the expansion of the universe. And so we saw earlier the Hubble parameter, so that is the rate at which the universe is expanding, and then related to that is also the deceleration parameter, which is how that changes as well. And so the Hubble parameter is just a function of the scale factor, and the Hubble constant is just evaluating that today. And so obviously any information we can infer about the universe we get from interpreting light from very distant objects. So if we want to accurately say something about the universe, we have to accurately interpret that light, right? And so we see that the wavelength, so the universe is expanding, and so it stretches the wavelengths of the photons. So the wavelength that it has when it is emitted to when we observe it increases, and that increased wavelength is called redshift, and it's related to the scale factor. So the luminosity distance and angular diameter distances are two ways of measuring distances in cosmology, because it's pretty difficult. You can't exactly take a measuring tape to like the Milky Way. So there are two ways you can do this. One is using standard candles. So these are objects that have intrinsic brightness, so we know how bright they are. So when we compare their intrinsic brightness to their observed brightness, we can infer its distance from us. And you can do the same thing with objects that you know how big they are. And these are standard rulers. And again, so if you compare the angular size that you observe compared to the intrinsic size that you know, you can again get a distance from that. So these are typically two very common ways in which we measure distances in cosmology. The dynamics of the universe is governed by the Einstein equations, and this is where the matter content of the universe comes in. So this is the famous Einstein equations. And I think if anyone was at the Open Day talk, and so Dr. John mentioned, I forget who said the quote, but essentially there's this beautiful quote that goes along the lines of space-time tells matter how to move, and matter tells space-time how to go. Is it up?
Yeah, it's John Wheeler.
John Wheeler, yeah. And so, and this is beautifully it sort of summarizes the Einstein equations quite nicely. And so the Einstein, so the left-hand side is your Einstein tensor, which is made up of your Ricci scalar tensor and your metric tensor, and the right-hand side is all your geometry, your matter system, so your densities, your pressures, and your fluid velocities. A homogeneous universe allows us to describe the matter as perfect fluids. So your stress energy tensor, so the T mu nu, that is a diagonal tensor, and you have some conservation laws. So your relativistic Euler and continuity equations come out of your conservation laws. That is covariant derivative. So anyone who's taken a course in GR will know that sitting in here are some lovely Christoffel symbols, and I'm not a particularly big fan of those. So the Friedmann equations, this essentially governs the expansion of the universe. And again, these actually come out of your relativistic perturbation theory. If you do the math, they come out of analyzing the Einstein equations. But again, that A dot over A you can just write as the Hubble parameter, and then you get the deceleration equation, and you can write at least the first Friedmann equation in terms of observational parameters. So that's sigma R0 and M0 and lambda0. These are the density parameters for radiation, matter, and dark energy. These all, you can measure all these things. So if you wanted to have some theoretical model in which you want to make some plots, for example, using some simulations, the parameters you would put in there actually have value. So it's quite nice to be able to map your theory to things that you can actually measure, right? And so for most of the universe's history, it has different evolutionary stages. And it's common to assume that in each of these stages, only one form of matter is dominated, and you can see this by the ratio of the energy densities in these different eras, right? So the W over there is an equation of state parameter, and so for radiation it's a third, for matter it's 0, and for dark energy it's -1. And so you see that in different stages of the universe, depending on which type of matter is dominating, the density evolves differently. Your scale factor evolves differently, which means the universe expands at different rates depending on which era in the universe you're in. And I've written the scale factor in terms of conformal time because you can also have conformal time, which is something I prefer to use conformal time as opposed to normal coordinate time. However, in order to actually describe what we see in terms of the matter distribution and the structure in the universe, we have to introduce inhomogeneities. And this isn't just something that we pull out of a hat or something like that. We actually see in the CMB, so its power spectrum is essentially fluctuations in the temperature, right? And so there are temperature inhomogeneities as early as 380,000 years in the universe's history. So it's not like we're just adding these things for fun to save a model. It's actually something we see. Gravitational instability plays a key role in inhomogeneity. So if you think about it, at some initial time, you have some inhomogeneity in the matter distribution. So there's more matter over here than over there. Where there is more matter where it's more dense, it's going to have a greater gravitational potential, so it will attract more, but because it can attract more, or because it attracts more, it can keep attracting more because it has a greater gravitational potential because of this. And so they always like to talk about, I think it's called the Matthew effect, about the rich getting richer and the poor getting poorer. And you can apply the same thing to gravitational instability. How we introduce this mathematically is through perturbation theory, and we can actually follow these perturbations as long as they are small in comparison to the background quantities. But as soon as they become comparable to the background quantities, the linear regime breaks down and you have to start considering non-linear structure formation. But I won't talk about that. So just to give you an idea of how this actually works, Newtonian gravity you can use as a sufficient description to model non-relativistic fluids as well as model sort of the universe on sub-horizon scales. And so the mass momentum conservation equations and Poisson equation, these are just standard sort of fluid mechanics equations that we use to describe our matter. And the idea is to take our density, our pressure, and our gravitational potential and perturb it. So you add, so the background quantities are everything with a bar, and then the delta, p, rho, and phi are your first order quantities. And so we do linear perturbation theory. We define the density contrast, which is a dimensionless parameter for the density. And you see, you get a new set of equations, and you can even write those in terms of all of your cosmological parameters. I haven't done that now. But the idea is then we can actually look, okay, well, if you manipulate those linearized evolution equations, you can get a second order differential equation that describes the evolution of your density contrast. So pick dark matter, for example. Cs squared is your adiabatic sound speed, and k squared just comes from doing the Fourier transform of the Laplacian. But dark matter doesn't interact with anything, well, not with anything, nor does it interact with itself. It only interacts gravitationally. So we model it as a pressureless fluid, and so we switch the pressure off, its perturbations, and the sound speed is also related to these things. So we switch all of that off. And we'll see that these, as we already saw in that table, that depending on which epoch of the universe you're in, these things grow differently. And so a nice way to show that is if you just consider a matter-dominated universe, the evolution equation has a particular form, and so the density for dark matter has both a growing and a decaying mode. So in a matter-dominated universe, you'll see that it's proportional, it grows proportional to the scale factor. In a radiation-dominated universe, this is quite interesting. So it's quite a subtle point where you actually have to consider both the density to the total density. You have to consider both radiation and matter. And the reason for this is that it is not anymore the dominant species anymore of matter, so you have to consider both. But it's not so clear in Newtonian perturbation theory. It's much clearer in relativistic perturbation theory. But you can kind of argue away the components that come from radiation. So you end up having a differential equation just in the matter perturbations. And so its solutions, so you have a constant solution or something that goes like from A, and in a dark energy dominated universe, it's either constant or it decays. So this is basically the idea, right? So you add perturbations to your system and you study how those perturbations themselves grow, because it is the growth of the perturbations, the initial inhomogeneities, that actually result in the structure that we see today. So you can do the same thing with relativistic perturbation theory. I'm not going to take us through the mathematics of this entirely. In fact, that BI is not even supposed to be there, so pretend that isn't there, right? So in the conformal Newtonian gauge, you can add perturbations to your metric, to your Robson-Walker metric, and in that you can, in the Newtonian gauge, certain parameters are switched off, which is supposed to include the B, so that's not supposed to be there. And so you should just be left with a plus phi and minus phi, which are your Bardeen variables. Technically it's phi and psi, but assuming adiabatic perturbations and etc., they actually end up being the same thing. But the idea is that we can now study the evolution of phi, right? And so with the Einstein equations, how you do the perturbation theory with that is you perturb your metric, you also perturb your Christoffel symbols, and then you also perturb your stress energy tensor. So it's not just perfectly diagonal anymore, you've got off diagonal elements as well. And they're split in different ways, but if you then actually analyze the conservation equations, you get relativistic versions of the quantum Newtonian equation. So the first equation is the relativistic sort of version of your matter perturbations and how they evolve. And the Einstein equations themselves, so if you just take the different components, the G, mu, nu, and the T, mu, nu, and you just give mu and nu values, you see you get these very famous set of equations, and they describe how the metric perturbations evolve, and they're obviously mapped to your matter content. Right? So these things are connected, and so you have this master equation for structure formation. This is a very popular equation. So the form of that equation, of course, changes depending on which era you're in, because the W will change, and of course your Hubble parameter, which is the curly H, will also change depending on which era you're in. So you solve the equation with initial conditions given the epoch that you're in. I'm going to say that lots of times, right? And so, yeah. Yeah, sorry. So this is very much shorthand. So the phi is actually a function of both conformal time in this case, and also of wave numbers in the K, right? But those are all conformal time derivatives. So time derivatives. And so to summarize this, you can look at, so depending on whether or not the wavelength of your perturbation lies inside or outside the horizon. So this is a difficult thing to try and understand. So essentially the Hubble radius is, or the horizon has at any point in time has a given length, right? And if your wavelength is greater than this, then it's considered super horizon modes. And if it's smaller, it means you're lying inside the horizon. And depending on whether or not you're inside the horizon or outside the horizon, it will grow differently. And it's also very important to note that the horizon is changing because the universe is expanding. And as the universe expands, the horizon changes. And so wavelengths will fall into the horizon. It's also very important then to keep track of when it is that they fall into the horizon, because it will evolve differently depending on when it falls in, right? And so your metric potential in the radiation era and the matter era, depending on what horizon, whether it's sub-horizon or super horizon. Yeah, this is just a summary. It will be clearer with the plots, right? So here's a plot. So you're plotting the ratio of the initial gravitational perturbation to the sort of solution that you get. And so you see the top line is super horizon scales. So that it's pretty constant except for the small sort of 10% drop, and that has to do with the transition between the matter and the radiation era. So you have some boundary conditions that relates the radiation era's potential to the matter era's potential. And that just results in a sort of 10% drop, but other than that, it's constant. And you see that at sub-horizon scales, it's sort of damps and oscillates pretty rapidly. So you see that with the A squared cos over there, right? And so for the evolution of the dark matter perturbations, you can again study this at super horizon and sub-horizon scales. Here the horizon was set at equality, right? So at matter radiation equality, so that's what the KE cube is. And you see again that depending on what scale you're considering, it grows differently. So this is cool and all, and we can study how these perturbations grow. But the idea is now to take this model of the universe that we have theoretically and try and map it to something that we can actually see from observational data. And one of those things is the matter power spectrum. So This is actually done in class, which is a sort of a numerical simulation thing package for cosmology. And roughly speaking, your matter perturbations are built into this power spectrum. And so you can plug that into class, and class will give you sort of a theoretical plot here. This one is just plotted over different redshift values. And so it's like, okay, well, those are theoretical predictions. What does the actual observation show? And the observation shows, well, it's not the worst prediction we've ever made. So all those binned points are the observational points from. So they use a combination of measurements depending on where in sort of on what scale it is that you're looking, because certain measurements are less accurate depending on the scale that they're considering. And so you see that, and so that solid line is a theoretical best fit that they get from their observational. So basically running a whole bunch of statistical analysis on all the data, you can get a theoretical best fit. But class does a pretty good job as well. And so those theoretical best fit values is actually technically what gets put into class, right? But you see that at least the theory matches the observation, which is quite nice to see. Another way of looking at this is to try and build the CMB power spectrum. And here, this is the CMB power spectrum. I don't know what happens to the y-axis, but okay. So this is the power spectrum in the CMB. So this is a plot that shows the fluctuations in temperature of the photons when they at recombination, right? And so again, in class, you can go in and you can vary the parameters over there. The matter density was varied, and so the peaks you see are shifted. It's like, okay, well, cool, that's nice. What does the data say? Well, the data tells us, well, this is the observational values for the power spectrum. And so what is quite nice about this is that the observation will tell us, okay, well, what we see right now is that the first peak has a particular height. And so if you have a model that is so far beyond that height, you should probably reconsider what you're doing. But if you're roughly in that range, you're probably doing a bit better than most. So what's nice about the observations is that not only does it give us an indication of how good our theoretical models are, but it also allows us to constrain the observational parameters that we plug into our simulations, right? And so we can not only have an idea of whether or not we're on the right track, but we can also turn our work into sort of more accurate versions of itself as time goes by. And so that is maybe it. I don't know if I took that last slide out. Yes, okay, I did. Okay, so if you're at all interested, there are some cool textbooks. The first one is Ryden's textbook. So this is very much a conversational textbook. It doesn't really deal with any of the relativistic stuff, but it's very good at conceptualizing everything. And I spent, I think, the first 3 months of my master's just reading this whole textbook, and it really helped my intuition for the science. And then you can tackle far more terrifying textbooks like Bauman and the Dodelson and Schmidt textbook. Bauman's book was based off his graduate course notes. I think he taught this course, was at Cambridge. And the Dodelson and Schmidt book is, I mean, it's Dodelson, the first edition, is certainly almost one of the most popular books to use and is known by most people. And then if you really want to go play around with some of these, the numerics, like the plots that we saw, you can use things like class, cam. I think CMB quick, I actually saw was actually used in a recent paper, which was surprising because I thought they kind of decommissioned that, but that was interesting. And yeah, thank you. That's it.
Thank you, Jaymie. If there are any questions, please feel free to ask now.
Also, I do know that there is that other talk happening at 2, so if you guys need to go, fine.
Actually, that was very interesting. Just in the Jaymie, you said we observe a lot of galaxies and stars and all these things. We observe a redshift, and that's always been the lab. Are there any cases in cosmology, astronomy, astrophysics where we observe blue shifts, and what does that mean for us then?
Not that I know of. There might be. I'm not actually sure. I think I don't know. I think it makes sense to me that maybe I don't know. I'm not going to say something. There might be. Yeah, please do.
Can I contribute to the
Sure.
Cool. On average, we've seen lots of observations, so that's really the overall picture on a very grand scale. This expansion, so the spectrum was longer wavelengths. But on a smaller scale, you see more random fluctuations. You have peculiar velocities of galaxies, which are their motion and superimposed on top of the overall expansion. So there you would occasionally see something really toward, but that's much more random. The overall picture is stuff's getting better.
Yeah.
From everything else.
Yeah.
What was this bubble radius you kept talking about? Is that like the observable, like the circle you draw around the observable radius? So you said like structure formation will take place differently whether you're inside or outside of the bubble radius.
Yeah.
Why?
That's a great question. I'm not sure, to be honest. So,
does it maybe have something to do with because it's further back in time, so structure formation earlier?
yeah, maybe. No, I actually haven't really thought about it in that way. Actually. But it's certainly, yeah, I'm not going to say anything before I ramble on that. Yeah. Yes.
The picture of the perturbation by various mode scale or green or that one.
Yeah.
So there is something like K sub EQ or whatever it is. So is there a particular mode, particular rate number that actually singles out certain solutions?
Yeah. So this particular one. So when you have to fix what you define as the horizon when you want to consider the growth of the perturbations, and in this case, it was fixed at matter radiation quality. So this wave number would correspond to that. And so because it's also changing with time, right? The Hubble radius, so this horizon is changing. So when you study these, you want to fix that. Study, yeah. So you could pick I suppose in principle you could pick a different one if you wanted to. Yeah. But in this case, it was at matter radiation.
Yeah. I don't know much about this, so thank you. Very interesting. I just had a question about I think it's your last class. So in your talk, you showed a few plots where you showed experimental data like that, and it has quite big error bars, which makes sense to me because it's experimental data.
Are you referring to this one?
Yes, but in this plot, there's this strange line where everything fits perfectly, and then suddenly it seems to be massive error bars.
Yeah. So this is so the L that you're plotting over there is called a multipole, and so a smaller multipole is larger scales, and so essentially you're looking further back, right? And if I remember, I think the term is called cosmic variance. I think we actually spoke about this yesterday. So, and this has got to do with our ability to actually observe the universe. So there's this sort of fundamental uncertainty in early time observations, just given the sample variance essentially that you have in this case. But for local universe stuff, so the things that are much later, so all of these that are so accurate, we have a much better idea, and the statistics are much more accurate at that point. So we have much, yeah, it's better explained.
That's not realization.
Yeah.
Where it breaks down.
Yeah, absolutely, sure.
Okay, if there are no further questions, yeah, let's thank Jaymie again. Thanks.